Good day, everyone. We will be considering Z transform in this lecture. Given an LTI system for which X, that is a discrete time linear time invariant system for which the sequence S of n is the input to the discrete time LTI system defined by the impulse sequence h of n. Then the output of n is the same as a convolution between h of n and s of n. Now, the analysis and representation of the system response y of n through the convolution sum is the linear combination of the shifting impulses defined as the sum of h of k, h of k, Sn is k, for k taking on values from negative infinity to positive infinity. So, excuse me, when the input S of n is the same as the eigenfunction z to the power of n, where z to the power of n is a complex exponential sequence, then the system response y of n be the same as for k, the summation of h of k z n minus k. For k taking on values from negative infinity to positive infinity. And here, if we expand this sequence, we get something like this. Now, the response can therefore be written as z to the power of n. K is the same, taking on values from negative infinity to positive infinity. H of k, z to the power of minus k. Now, this is the same, same lambda, z of n, z to the power of n, which is the same as h of z h of z zn. That is h of z, which is the same as lambda, which is the eigenvalue and the impulse response of the system in the frequency domain, is the same as k taking on values from negative infinity to positive infinity, h of k z to the power minus k is the z transform h of n. So in general, given a discrete time linear time invariant system, then the z transform, let's put it this way, given a linear time invariant system for which the eigenfunction, or better still, the input sequence is the same as S of n. Then the Z transform S of Z be the same as S of Z being the sum and taking all values from negative infinity to positive infinity. S of n with the power is the Z transform. Z transform of S of n. So just like we mentioned in our previous lecture, that the Z transform is the discrete time counterpart of the Laplace transform. So we can now define the inverse Z transform. Just like the Laplace transform, the inverse Z transform is the inverse Z transform S of n is given as an integration in the Z plane such that S of n is the same as 1 over 2 pi j integration over the contour S of z z n minus 1 z, where c is a counterclockwise contour of integration. Counterclockwise integration enclosing the origin. So for ease of evaluation, as in the case of Laplace transform, the table of Z transform pairs is used for the estimation of the inverse Z transform. Okay. Now, let's talk about the region of convergence. Now, the region of convergence on the Z-plane. Now, notice that we talk of Z-plane, while in Laplace transform, we talk of the X-plane. So the region of convergence on the Z-plane is the region where the Z transform is finite. Okay? There's a region of convergence on the Z-plane. It's the region where Z transform, where the Z transform is finite. So that is, it is the range of values, of the complex Z for which the Z transform converges. Now, you will observe that the X-plane looks something like this, where this is the imaginary S and this is the real S for the S-plane. Okay. Now, for the Z-plane, We also have the imaginary and the real axis, the z, but you will observe that the j omega axis, which is the imaginary axis, right here in the x-plane, maps to the unit circle in the z-plane using the transformation z is the same as e j omega, such that when you fold the j omega axis is the j omega axis. Now, when you fold it into a circle to look something like this, then you have the z-plane. So in other words, the imaginary axis here is folded into a circle where this is the imaginary z, okay? Though we still play this arrow for necessary convention, okay? So in other words here, at this point, and also at this point, and also at this point, we have the high positive frequencies. Then at this point, and also at this point, we have the high negative frequencies. Then at the origin, we have DC, while at this point, we have the zero frequency, the DC. Okay, so while we have this for the S-plane, then the Z-plane looks something like this. So don't forget that in the Z-plane, the j omega axis is seen to fold into a circle. So what are the properties of the region of convergence? Just like in Laplace transform, properties of the region of convergence. So the first point here is that the region of convergence never contains any pole. So region of convergence never contains any poles. So in other words, if we have, for instance, this is the imaginary axis, imaginary z, this is the real z. So let's assume we have a pole here and we have a pole here. Now, so long we have a pole here, then the region of convergence must exclude the internal pole such that this becomes the region of convergence. S, there is no region of convergence because it must never contain any pole, no matter the number of poles we have in here, okay? Now, second point to note is that if the input sequence S of n is right-sided, like we mentioned in our previous lecture, so meaning it is multiplied by a unit step function such that the negative part reduces to 0, so we have 0 to positive infinity, okay? And otherwise, we have 0 to negative infinity. That is, when the unit impulse response is of the form minus 0 n. Okay, so means we have from 0 to negative infinity. So this is going to give us left-sided signal, while this is going to give us right-sided signal. Okay, so if the input sequence is right-sided, then the region of convergence is the area outside the circle. That is Z, mod Z is greater than alpha, for instance, where alpha is the same as the outermost pole. So when we have something like this, in the previous example, we have one pole here, another pole here. So if this is alpha, then this is right-sided, meaning Z is greater than alpha. Then the region of convergence is the area outside the circle. That's the region of convergence. Now the third point here is if the input sequence is left-sided, that is, we have this form multiplied by the signal, then the region of convergence is the area inside the circle. So that is mod Z is less than alpha, where alpha is the same as the innermost pole. So here, something like this. So this is the innermost pole, because don't forget the first point, the region of convergence never contains any pole. So this becomes the region of convergence, okay? This is ROC, the region of convergence, okay? And this is imaginary Z, this is real Z, this is imaginary Z, real Z, and here mod of Z is less than. Okay, so the fourth point here for property is that if the input sequence is two-sided, or better still, the sum of left-sided signal, sided, and right-sided signal the region of convergence is either donut, that is alpha is less than mod Z is less than beta, or else the individual region of convergence will not overlap. So producing a null. Okay, so it means something like this. So let's say this is alpha and this is beta. So the region of convergence will be something like this. So it forms a donut. This is the region of convergence. This is when alpha is less than mod z, less than beta. So it means z, okay, that's that. Then if otherwise, then something like this. So meaning there is no overlap. Okay. Okay, so we have alpha, so cleaned up, then we have beta here. So this is greater, so it comes out. So this is less than, so it comes in here. So z is less than beta here, so it comes into it, while z is greater than alpha, so it goes up. So it forms a dot. Then the fifth point here is if the sequence is a finite duration, then the region of convergence is the entire x-plane, z-plane rather, sorry, excluding s equal to 0, minus infinity, and positive infinity. So we have something like this. It's imaginary axis, imaginary z, real z. So here we're excluding negative infinity, 0, and positive infinity, right? So every other part of the z-plane is a region of convergence. Well, these are the properties. And recall that we talked about zeros and poles in Laplace transform, and I think the analysis follows directly. Also, zeros and poles and zeros of Z transform. So here you note that the zero is a value that forces the Z transform to 0, because we have S of Z is the same as, say, Z1 minus 1 minus K, Z2 minus K1, K2, for instance, all the way to Z3 minus Kn over the roots P1 minus L1, P2 minus L2, all the way to this n, Pn minus Ln. Here, when we set Z1 minus K to 0, when K is the same as Z1, that is Z1 is the same as K, okay? So K is the same as Z1, then this is forced to 0. And if this is 0, then the whole of the Z transform reduces to 0. So a 0 is a value that forces the Z transform to 0. And also, A pole is a value that forces the Z transform to infinity. Okay, so if P, for instance, P1 minus L1 is 0, so it means that P1 is equal to L1. So when P1 is equal to L1, then this is 0. And once we put this into 0, so it means the Z transform will be what we have as the zeros divided by 0. And anything divided by 0 extends to infinity. So a pole is a value that forces the Z transform to infinity. And one thing we did not mention in Laplace transform, which also applies to Laplace transform, is that the zeros are designated using a circle on the z-plane. Okay, so we designate it on the z-plane by a circle. It's real. See, why we designate a pole by a star sign, okay, or an X sign. This is imaginary z. This is real z. So we'll look at a few examples. Now, let us evaluate the Z transform for the sequence defined as follows. This is 3. This is -1. This is 2. This is 0. So we have -1, 0, 1, 2. Now recall that the Z transform is given by the Z transform is the same as sum of n taking values from negative infinity to positive infinity. So n z minus n. But in this case, we have n taking on values from -1 to 2. Okay, such that s of z is the same as n equal to -1 to 2 s of n z. So when n is the same as -1, now the magnitude here is 3. So s of n is 3. Then z will be, here n is -1, so it will be minus -1. So at this point, n is equal to -1 plus, and the magnitude is -1, -1, zn, so this is 0, so minus into 0, right? So at this point, we have n equal to 0 plus, when n is 1, magnitude is 2, 2, z, then minus n, that's 1, minus 1, plus, this is n equal to 1. At n equal to 2, the magnitude is 0. So that will be 0 times z minus n is 2, that will be minus 2. This at n equal to 0. So this will reduce to 3z to the power of 1 minus z to the power of 0 plus 2z minus 1. So everything there is 0 plus 0. So anything to the power of 0 is 1. So the Laplace transform become 3z minus 1 plus 2z to the power of minus 1, which is the same as 3z minus 1 plus 2 divided by z. That's simple. Okay, consider another example. So if we have s of n to be the same as 1 over 4 to the power of n, u of n, so we know this is a right-sided signal because it is multiplied by a unit step function. It looks something like this. Okay. So the Laplace transform, therefore, becomes summation here, n equal to minus infinity to positive infinity, s of n, z minus n. So this will be the same as summation n equal to minus infinity to plus infinity. If we plug in that here, 1 over 4 n u of n z minus n. Now that we have multiplied by the unit step function, then the limits will be altered because negative infinity to 0 is cancelled out. So the limits will now be from n equal to 0 to positive infinity. So that will be n equal to 0 to infinity, 1 over 4 to the power of n, z minus n. And we can rewrite this as n equal to 0 to infinity, 1 over 4n, z minus 1 to the power of n. So if we compress that, so we have n equal to 0 to infinity, 1 over 4, z minus 1 to the power of n. Good. Now, you will recall that the sum of infinite geometry is the same as n equal to 0 to infinity a rn, or when the limit is taken from n equal to 1 infinity, then it is a rn minus 1 is the same as a over 1 minus r. Here, a is the first term, while r is a common ratio. Okay, so in our case, this cuts it. This, which is equivalent to this, and this is equivalent to this. Okay, and where r, let's put it here, r is the same as 1 over 4 z to the power of minus 1. Okay, so here n is the same as n, then a is 1, so equal to 1, right? That's the coefficient. So if we plug in this into this, so our a is 1 minus r, then the Laplace transform s of z will become 1 over 1 minus 1 over 4 z. So 1 over 4 is 0.25, so this will be the same thing as 1 over 1 minus 0.25 z inverse, which is the same as 1 over 1 minus 0.25 z, which is the same as z over z and 0.25. Okay, so now if you look carefully, when z is equal to 0.25, then the Laplace transform will be forced to 0. And we know that the region of convergence is that region where the z transform is finite, it's less than infinity, it's finite. Okay, so hence mod of z must be greater than 0.25 for convergence. So to designate the Z transform properly, or appropriately or correctly, then Laplace transform is the same as Z over Z minus 0.25 for values of mod of Z greater than 0.25. Okay. Now that we have done this, let us look at some verifiable Z transform pairs and then solve a few problems. So here are some of the verifiable Z transform pairs, and let us play with an example. So let's assume S of Z, the Z transform is given as 1 over 1 minus 0.25 Z units. So this is going to be the same as, okay, let's expand this a bit. Okay, say plus 1 over 1 0.5 Z for values of 0.25 less than Z less than 0.5. So in this, it means Z is greater than 0.25 and Z is less than 0.25. So from the transform pairs, when Z is greater than A, we have a right-sided signal because this is of the form 1 over 1 minus AZ to the power of minus 1, which is for which A is 0.5, so it's similar. So we have a right-sided signal when Z is greater than mod A. So that would look something like AN. And when Z is less than A, and of this form, we have something similar to this, and that is minus AN to half N U of minus N minus 1. Perfect. Here A, in this case, A is 0.25. In this case, A is 0.5. So once we plug that in, we have S of N to look something like this. 0.25 of N of N plus into bracket minus 0.5 N of minus N minus 1, which will be the same as 0.25 of N of N minus 0.5 N U minus N minus 1. Okay, so we know this is the same as 1 over 4 N 1 minus 1 2 N minus N. So we can equally plot the region of convergence here because we have a pole. We have a pole here at Z equal to 1 over 4, say 1 over 4, and at 1 over 2. Okay, good. And since this is a right-sided signal, is a right-sided signal, and this is a left-sided signal. So for a right-sided signal, the region of convergence goes out, right? So the outermost side. Now, but for a left-sided signal, the region of convergence is the other way around. It comes this way. So in other words, we have a donut shape looking like this. Yeah, this is the region of convergence. Okay. So let us look at some other examples. Some other examples. So let's assume we are given S of n to be the same as 1 over 2 and n is 1 over 3. So in this case, both of them are right-sided signals. So we know that this is of the form this, right? Yes, so this form. So we can write the Laplace transform to be same as 1 over 1 minus 1 over 2 is a here, 2 plus 1 over 1 over 3. Okay, this now will be the same as z over 1 minus 1 over 2 plus z multiplying by z divided by z over z minus 1 over 3. So if we take the LCM here, we now have z minus 1 over 2, z minus 1 over 3, to that z into bracket z minus 1 over 3 plus z into bracket z minus 1 over 2. So this will give us z squared minus z over 3 plus z squared minus z over 2 divided by z minus 1 over 2, z minus 1 over 3, and to give us 2z squared minus 2z plus 3z divided by 6 divided by z minus 1 over 2, z minus 1 over 3 should be the same as 2z squared plus 5 z over 6 divided by z minus 1 over 2, z minus 1 over 3, and this will give us 2z. If we bring 2z out, that will be z times z squared minus 5 over 6 divided by z minus 1 over 2, z minus 1 over 3. So here we have the zeros up here, zeros, then we have the pole at the denominator, right? So in this case, when we equate the roots to 0 for the 0, so the first root here is 2z, so we say 2z is equal to 0, then 0 divided by 2, then z is equal to 0. Then the second root here is z minus 5 over 6 equal to 0. So it means z is equal to 5 over 6. Now for the poles, you have two roots too. So that's z minus 1 over 2 is equal to 0. So when this crosses equality sign, so z is equal to 1 over 2. And the second pole here is z minus 1 over 3 is equal to 0. That crosses equality sign, z is equal to 1 over 3. So in this case, we have two zeros. So we have two zeros. That's at z equal to 0 and at z equal to 5 over 6. Then we have two poles, right? That is at z equal to 1 over 2 and at z equal to 1 over 3. Perfect. So if we draw the z plane, this is the imaginary z, this is the real z. So we have some zeros. Let's use a different color for the zeros. We have a 0 at 0 and a 0 at 5 over 6. That's about 0.416, right? So let's say we have that at somewhere around here, 5 or 6. So remember we said we use circles to denote zeros and we use x sign to denote poles. So then how many poles do we have? We have two poles. So we have a pole at this. So 1 over 3 is about, let's use another color. Okay, let's use blue. So 1 over 3 is about 0.33 or so, yeah. And 1 over 2 is 0.5. So we have a pole at somewhere here. So there's a pole. It's less than 5 over 6. That's 1 over 3. Then we have another pole here. The 0.5 is larger than 5 over 6. I don't know, 0.416. We have another pole here at 1 over 2. And recall that a pole must never include any other pole. And here we have z to be greater than 1 over 3 and z to be greater than 1 over 2. So it means that the region of convergence of 1 over 2 and 1 over 3 and 1 over 2 overlap. But since the region of convergence must not include any other pole, so the region of convergence will be the region outside 0.5. So this will be the region of convergence. So region of convergence, because the region of convergence must never contain any other pole, so it must not contain this pole. So it's going to be all of those sides. Okay, that is clear. So let's take one more example before we call it a day. So let us consider this example. S of n is the same as 1 over 3 n, okay, plus 1 over 2 n minus n minus Okay, so we can compare this. So this form, y, this is of this form. So it means that here, mod z is less than 2. Y here, mod z is greater than 1 over 3. So go further into relating both, recall, okay? And once we relate both, then we are fine. And look carefully, this is a negative sign here. And here we do not have the negative sign. So once we plug in the negative sign, so it means we're going to have 1 over 1 minus 1 over 3 z minus, because minus times plus is minus, so 1 over 1 minus 1 over 2 z. So just like we did in the previous example, so 1 minus 1 over 3. Okay, let us expand first. Let us simplify. Let us simplify. So if we simplify, this is the same as z over z is 1 over 3 minus 1 over, sorry, minus z is minus z divided by z minus 1 over 2. So now that we have that, we can take LCM here, then here we go. Z minus 1 over 3, z minus 1 over 2, and that will be z into bracket z minus 1 over 2 minus z into bracket z minus 1 over 3. And then this will give us minus 1 over 6 z over z minus 1 over 2 z minus 1 over 3. And then recall that here z is greater than this, so the condition here for convergence is that z is greater than 1 over 3, which is less than 1 over 2. So highlight the poles and zeros. So for the zeros, this is a constant. So for the zeros, we have just 1 0, which is z equal to 0. And for the poles, we have 2. At z minus 1 over 2 equal to 0, so z is the same as 1 over 2. And at z minus 1 over 3 equal to 0, then at z equal to 1 over 3. So we have 2 poles. We have 1 0, that is at z equal to 0. Then we have 2 poles at z equal to 1 over 2 and at z equal to 1 over 3. Okay. So now we can verify the region of convergence. So we have a 0 at 0. This is the imaginary z. This is the real z. Then we have a pole at 1 over 3, and then we have a pole at as 1 over 2. So here we have 4. So if we have this here, 1 over 3, then we have this here for 1 over 2, then we know that this is a right-sided sigma, 1 over 3 for z greater than 1 over 3, and by the rule, the region of convergence is outside the circle. Okay, and now at z less than 1 over 2, we know the sigma is left-sided, so the region of convergence is inside the circle. So here we have a donut, and we know the region of convergence must not contain any other pole, so it cannot go beyond this pole placement here. So this is the region of convergence. So the region of convergence is at 1 over 3 less than z less than 1 over 2. Well, I think this is a good place to stop, and bye for now.